Hello again. This is kind of an interlesson that I've decided to put in because Chemistry 30 assumes that you've taken Chemistry 20 recently and that you remember a fair bit of detail about intermolecular forces. And we don't have a big review about that, which is mostly fine, except that in the organic chemistry section, they start to ask some questions about melting and boiling points, and you really can't negotiate that unless you know some things about intermolecular forces. So let's talk about this for a bit and try to get some basic information into you. So when we have a bunch of molecules, and I'm drawing ones that kind of look like water, but they could be anything. First of all, there are two classes of forces that you can talk about when you've got a bunch of molecules. One is the forces inside the molecules that hold them together. So over here we have this central atom attached to two other atoms. These lines I'm drawing in deep red are the ones inside the molecules that hold them together, and those are called intramolecular forces. Intra means inside one. If you did intramural sports in school, that means sports just inside your school, your students playing against some more of your students, no other school is involved. Here, intramolecular means inside a single molecule. So this molecule has intramolecular forces, so does this one, and so does this one. Those forces just hold like the arms of a molecule onto its body, that sort of thing. Also, inside a molecule, or sorry, besides the forces inside a molecule, this top left molecule might have some kind of attraction to the molecule at the bottom, and it might have some kind of attraction to the molecule over there. Each of these might interact, and the forces between a couple of molecules are called intermolecular forces. If you know what international means, that means between one nation and another nation. Intermolecular is between one molecule and other molecules around it. So there are bonding forces that hold molecules together, and that's mostly not what we're talking about in this section. We are interested in the forces between one molecule and the other molecules around it. So hopefully that part's okay. Let's create a little space here, and we're going to be looking at three different types. These do break down further, but there are three major categories of intermolecular forces that we want to get into. And I'll give you all the names first before we dig in. There is a force called, hard to draw with the eraser, London dispersion force. There is a force called dipole-dipole force. And the last one we look at is hydrogen bonding force. I'm going to skim over a fair bit of detail in here because I don't want to spend a huge amount of time on this, and I don't want you to spend a lot of time on it either, but I'm hoping I can give you enough that you can go into the questions and feel at least decently prepared. And if you want more, YouTube is at your service, and so are your instructors if you feel like you need more info to move on. So, let's start with the first of these. London dispersion force is a force between a molecule. I'm just going to draw the molecules like balls now, just so we don't have to draw complicated shapes. If we have purple ball and green ball, these are made of atoms, which means they contain protons on the inside and electrons on the outside. Let's actually put some electrons around that and make this a little bit easier. So here we have a positively charged nucleus and negatively charged electrons around it. And for the burgundy one, we also have a positively charged nucleus and negatively charged electrons around it. London dispersion force, really briefly, is my protons attract your protons attract my electrons. There's an attraction between the positives of one atom and the negatives of the atom next to it. And these forces, you would think that all these forces would cancel out, but it turns out that as these electrons move around, there are what they call temporary dipoles that come into existence where the charges get slightly out of balance, and that force tends to be attractive. It tends to pull these atoms together. And so the overall effect, the part that you really need to remember, is that I'll put my positives attract your negatives, and vice versa. Your positives attract my negatives. Every atom has positive charges, and with the exception of hydrogen ions, every atom has electrons, so every atom has this. Everything has London dispersion force. And so even though it's not an extremely strong force, everything has London dispersion force, and that means it's very important. When we are looking at some type of matter and say what forces are present in this substance, you can say London dispersion force without even thinking, because it's in everything. It is generally considered the weakest of these three forces, but because it's present in everything, it's always a factor of some kind in how strongly the molecules stick together. And the other thing to know about it is the more protons and electrons you have, the stronger it gets. So weak, but, fun word, ubiquitous. That means it's everywhere. And the more protons and electrons you have, the stronger it gets. So hydrogen has super weak London force, helium has more, lithium has more, beryllium has more, boron, carbon, nitrogen. Every time an element gets bigger, it has more London dispersion force. And I'll just say it scales with atom size. So if you have two substances with London dispersion force, let's say you have chlorine and fluorine. Let's see if I can get this right. I believe fluorine atoms have 9 electrons each and 9 protons each, so there would be a total of 18 charged particles in each fluorine. Chlorine atoms have 17 protons and electrons each, 17 each, which would mean 34. So just comparing this, chlorine should have stronger London dispersion force because it has more charged particles in it. That's the kind of comparison you can do to get a rough idea of who has more. And that's about all there is to say about London dispersion force. So we're something like a third of the way done already. Right? So everything has it, scales with atom size, and it is the weakest force. So if an atom has dipole-dipole or hydrogen bonding force, we'll consider that to be more important. But London force is always in there. We always have to think about it. Okay. Do you remember what polar molecules are? We talked about this a fair bit in Chem 20 if you ever took that. Let's assume you don't. If we have two atoms like chlorine, Cl2, chlorines have 7 valence electrons, which go 1, 2, 3, 4, 5, 6, 7, and the other atom has 1, 2, 3, 4, 5, 6, 7. I should have made those colors more different. Sorry about that. Each of these atoms wishes it had a full octet. They were born with 7 electrons, and they spend all day thinking, I wish I had 8 electrons. That would be amazing. If only I could get 8 somehow. Well, if these atoms link together, I don't know if I can move this, but let's give it a shot. Nope, not happening. If these atoms drifted towards each other and shared these two electrons, then through the magic of sharing, they could each kind of have 8 electrons. This chlorine would have 2, 4, 6, 7, and this electron isn't exactly his, but he can pretend, and that could count as 8. And this atom could say 1, 2, 3, 4, 5, 6, 7. This one isn't exactly hers, but she can pretend a little and say that she has 8. If they do this, then they each have 8 electrons, and now they have a full octet and they're happy. And if these are two identical chlorine atoms, I have to redraw this slightly, and they're sharing these electrons, the electrons will end up dead center between them. That last pair of electrons will end up exactly in the middle between the two chlorines. Now, let's try another one like that. What if we have salt, sodium chloride? Again, when these atoms bond, there's a pair of electrons that is shared between the two of them, but it turns out it's not shared equally. And the reason for this is atoms are always pulling on the electrons that they're sharing and trying to take them back. In a case like this where the atoms are identical, nobody can win that fight and the electrons end up dead center. But if you check your periodic table, there is a number called the electronegativity that tells you how hard each of these atoms pulls on shared electrons. For chlorine, quick pause while you grab your periodic table. Chlorine is element number 17. It says Cl, and right above that is the number 3.2. 3.2 is chlorine's electronegativity, and it tells you how hard it pulls on electrons that it's sharing. This by itself doesn't tell us anything, but if we look up sodium, which is element number 11, over on the left column, its electronegativity is only 0.9. And these numbers by themselves don't tell us much, but when we see them together, we see, okay, a 3.2 versus a 0.9, chlorine is way stronger than sodium is. And because of that, these electrons are not going to be shared equally. They're not going to be dead center. They're going to be way over toward the chlorine. And that means the chlorine ends up with a net negative charge because it's got all these electrons shifted toward it. And the sodium, whose electrons have pretty much abandoned it, ends up with a bit of a positive charge. It's not that there's extra charge, it's that the charge that they have is out of balance or unequally shared. And when that happens, we say that this substance is polar. Polar as in it has a positive pole over on the sodium and a negative pole over on the chlorine. We care about that because if you have a whole pile of these compounds with positive ends and negative ends, they stick together like magnets. If you put all these in a pile, the positive from one will stick to the negative of another, and they'll all end up networking like that, and they lock together really strongly. And when that happens, you get something that's difficult to pull apart because the positives and negatives are all attracted. So polar means sticky equals strongly attracted to each other. Attracted to each other. All these forces are attraction to each other, but dipole-dipole force means there's a strong attraction between these because of the plus ends and the negative ends. And that happens because the electronegativities are really different. With chlorine, the electronegativities were 3.2 and 3.2. There was no difference, and so we could say this molecule is not polar at all. The difference is 0. They're evenly matched, and that would mean the electrons end up dead center. They love mom and dad equally. In this pair, these electrons are mostly over toward mom. They spend all their time on that side. They haven't seen dad in weeks because there's much stronger attraction for this side of the molecule. So comparing those electronegativities is how you decide if something is polar or not. Now, let me just give you some notation about that. We have some symbols that we can use for this. If you have something like sodium chloride, instead of drawing the little dots and trying to decide how far over to put them, the symbol they generally use is a little arrow that points in the direction of the stronger electronegativity, the higher one. They usually put a little tick mark across that arrow. So this tells you electrons shifted this way. And the difference between these electronegativities, if you do 3.2 minus 0.9, that tells you chlorine is stronger by 2.3. So sometimes people will write this arrow with the tick and they'll put 2.3 above it just to indicate how big of a difference in electronegativity is there. And the most complex way you can write this is they do a kind of loopy D like this. It's a Greek lowercase delta. And they'll put delta equals 2.3. And, last thing, I promise, this difference in electronegativities is called the bond dipole. Tells you how much of a difference in electronegativity there is. So, if you see a difference of like 0.1, 0.2, that means, okay, the electrons are out of balance, but only a little bit. 2.3 is a pretty substantial difference, tells you that the chlorine is really hogging those electrons and they spend very little time with the sodium. And just for fun, check your periodic table. What do you think is the biggest difference you could possibly get for a bond dipole? What's the biggest mismatch you could possibly have? You'd have to find the atom with the highest electronegativity and the atom with the lowest. If you look in the top right corner, fluorine is the champion. It has an electronegativity of 4.0, really, really strong at attracting electrons. And if you look in the bottom left corner, francium is rated at only 0.7. So francium fluoride would be the most polar compound that you could get, pretty much. 0.7 to 4.0 would be a bond dipole of 3.3. And with the elements we currently know about, you just couldn't get a bigger difference than that. So when you see 2.3, you go, oh, okay, that's getting close to the maximum. If you see a 1, not so impressive. If you see a 0.2, that's hardly anything. All right, so when a substance has big electronegativity differences, that means the bonds inside it are polar. And I wish that was all there is to say about dipole-dipole, but there is a little more. Sorry, this one is the hardest one. Hydrogen bonding is pretty easy. But I have to throw more at you about dip-dip force. Did I mention dipole-dipole is sometimes shortened down to dip-dip? If you have a compound like chlorine, we could say that has the same electronegativity. That's too thin. Same electronegativity, so not polar. That's an easy example. Something like sodium chloride, we've seen that is polar because you have a difference in electronegativity. Different electronegativity, polar. But there's one more thing to think about, and that's the overall shape of the molecule and whether it's symmetric or not. Because here's something that can happen. Think about methane. Methane is CH4. And I'm going to lie slightly about the structure and draw it like it's flat. It's actually a tetrahedron, but pretend with me for a moment. This will make a valid point. It's not as much of a cheat as you might think. Question: is this polar? Well, if you check electronegativities, carbon's electronegativity is 2.6, and the hydrogens are 2.2. So that means all the electrons in each of these bonds should be shifted inward toward the carbon. So it's got four identical bonds, all of which are polar, and they're all in toward the carbon. So that sounds like it should be polar, and yet methane is nonpolar. So what's going on with that? If you know what vectors are, then you've probably already seen what's going to happen. It turns out if you have an electron shift downward and an exactly equal amount of electron shift upward, and then you have an electron shift to the right and another electron shift to the left, all of those cancel out, and you end up with a molecule that's not polar. This is symmetric, so dipoles cancel out, and that makes it nonpolar. Anytime you have equal and opposite dipoles, they cancel out and it's like they don't exist. So methane looks like it should be polar. You could say it has polar bonds, but overall it's nonpolar because they cancel out. Another example of that, carbon dioxide, is shaped like this. We have electrons shifting to the left towards that oxygen because 3.4 is higher than 2.6, but we have the exact same thing happening in the opposite direction, and so these dipoles are identical in opposite directions. They cancel out. Carbon dioxide is nonpolar. So if they have the same electronegativity, they're not polar. If you have electronegativity differences, that means they're polar. And last thing, unless the molecule is symmetric. If it's perfectly symmetric, then it can be nonpolar. So for some molecules, you'll have to do Lewis structures, figure out what the shape of the molecule is, and that will help you decide, is symmetry even possible? And that will tell you if it's got dipole-dipole force, and that can tell you what you can expect for its melting and boiling points. Last one of these, and as I promised before, this one is relatively short. Hydrogen bonding. Hydrogen has a special trick when it comes to this. When you have a compound with hydrogen in it, a hydrogen atom consists of a single proton and around it a single electron. If you give hydrogen more electrons, that's fine. Nothing really special happens then. But if you take away hydrogen's electron, you end up with a pure positive charge. Because a hydrogen is one proton and one electron, if you pull this electron off, what you have left is, this is a glowy, shiny effect, a proton with no negatives around it at all. And to drive that point home, they actually do call this sometimes a naked positive charge. It's a plus with no negatives screening it whatsoever, and this is a very attractive to negative charges. It produces like a super dipole-dipole force because it's a positive with no negatives in the way. It pulls on negatives harder than anything else does. So if you can pull hydrogen's electron way far away from it, you can produce this hydrogen bonding force. Very attractive to negative charges, and that makes it very strong. The strongest of these three forces, in fact. Very strong exclamation mark. So when does that happen? Well, there are three atoms that can do this, and they are NO and F. They're all in the top right corner. Nitrogen, oxygen, and fluorine are the only ones that can do this trick. It's a combination of, they're fairly small in size, so their charge is very concentrated, and they have very high electronegativity. So anytime you have a hydrogen bonded to nitrogen, oxygen, or fluorine, you can expect hydrogen bonding force. It's like super dipole force, and it makes molecules that have it very sticky. Now, one more thing about this. If we have, I'm trying to think of a good example for this. We can ask you questions like CH3F. In a question about bonding forces, we could give you a chemical like this. This is fluoromethane, and say, what forces does this have inside it? And you'll say London dispersion force, of course, because everything has that. Dipole force, well, if we've got carbon, hydrogen, 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 fluorine. What do you think? Is that polar? These bonds are polar. We have 0.4 towards the carbon, zero point 0.4 toward the carbon, 0.4 toward the carbon, and 2.6 versus 4 is 1.4 toward the fluorine, so our dipoles look like this. Do they cancel out? Careful. When we had methane, this was symmetric because all the bonds were identical, but look here. We have a shift to the right and a shift to the left. These two will cancel out, but then we have electron shift down and then another electron shift down. If we had a down and an up, those would cancel, but these do not. This molecule is not symmetric. The fluorine messes up the symmetry. So this is not symmetric, so yes, it is polar. And the last question they could ask is, does it have hydrogen bonding force? And the wrong way to look at this is to go, there's hydrogen, there's fluorine, yes it does. But look out, you have to have the hydrogen and the fluorine bonded to each other, and that's not the case here. They're in the same molecule, and that is not enough. This hydrogen is bonded to a carbon. All the hydrogens are bonded to carbon, not to fluorine, and so this has no hydrogen bonding. So if they asked if this has the three forces, you'd say yes, because everything does, yes, because it's asymmetric, and no, because the hydrogen doesn't touch the fluorine. So don't just look at this, please. Make an actual sketch of the molecular shape, and from that you can decide, is your H bonded to your N or your O or your F? Sound good? There's a lot more to be said about these. I am not an expert on this topic, so I hope this is enough for you to at least attempt the questions in the organic unit, and I'll be there with you for those. If there's any other gaps, I will try to patch them as we go. See you in the next one.